Everyone. In this video, we are going to go over the role of the solvent in SN2 and SN1 reactions. Now, last time we talked about the role of the nucleophile, and we said that a nucleophile has to be less bulky and unstable for SN2 reactions. So the nucleophile is better if it is less bulky and unstable. Now, by unstable, we mean that the nucleophile has a lot of energy and it really wants to react. We also talked about the role of the nucleophile in an SN1 reaction, and we said that it doesn't matter. Because the rate of the reaction does not depend on the nucleophile, it only depends on the substrate and the leaving group on that substrate. So let's talk about nucleophile strength, and I guess this will more so apply to an SN2 reaction, at least at first. So let's look at a few different nucleophiles. Let's compare two negatively charged nucleophiles. So we have OH minus and NH2 minus. Now let's try to figure out which one is stronger, or which nucleophile is more likely to react. Now looking at these two, we're really comparing oxygen and nitrogen. So if we're in the same row, typically what we're comparing is the electronegativity of these atoms. So which atom is more electronegative, oxygen or nitrogen? Oxygen. And then nitrogen is less electronegative. And I'm just using En as an abbreviation for electronegative. So if nitrogen is less electronegative, is it happy with that negative charge? No, it would prefer to give up those electrons or share those electrons. So that's actually going to make NH2 minus more reactive because it doesn't really want those electrons as much as oxygen wants electrons. So comparatively, NH2 minus will be more unstable. It wants to give up those electrons, so it's going to be the better nucleophile. So let's kind of write a summary of that. So nitrogen is less electronegative and wants to react, and it wants to react to share those electrons. So that means it's less stable, and that means it's the better nucleophile. Okay, so now let's compare two neutral nucleophiles. So let's compare H2O and NH3. So we're just adding on a hydrogen to each of those nucleophiles that we looked at first. So now they're neutral. And now let's see if we can figure out which nucleophile is stronger. So any guesses? So this will actually be similar to our first example, so nitrogen is still less electronegative, and oxygen is still more electronegative. So because nitrogen is less electronegative, it will hold on to that lone pair of electrons less tightly than oxygen will. Oxygen loves electrons, so it's okay with those lone pairs. It doesn't really need to share them or give them up. Nitrogen is less fond of electrons, so it's going to want to share its electrons more so than oxygen. So less electronegative and wants to share electrons. So it is less stable and more likely to react. So again, the nitrogen containing molecule is the better nucleophile. Now, what if we're comparing a neutral nucleophile to a negatively charged nucleophile? So let's compare H2O and OH minus. Which one do you think will be the better nucleophile? Or another way to ask this is, which one is less stable and more likely to react? So remember, if atoms are neutral, they're usually pretty happy, they're pretty stable. But if an atom has a charge, it's usually less stable. So in this case, because OH minus has a negative charge, that means it is less stable and it wants to react and give that negative charge or the extra electrons to something else or share it with something else. Now, again, we're comparing a neutral molecule to an ion here, whereas before we were comparing two molecules with different atoms. So it kind of depends on what you're comparing and what makes the better nucleophile. But typically you want something that has a negative charge or something that is less electronegative and wants to share its electrons. Now, if you want a little more detail on what makes a good nucleophile, there's a website at the bottom that I've listed. This is on masterorganicchemistry.com. They have a lot of really useful tips and tricks for organic chemistry, so I recommend you check out that website, particularly their page on what makes a good nucleophile. Okay, so we just compared nucleophiles that have atoms in the same row. What about if you're comparing nucleophiles that have atoms in the same column? So let's talk about that. Okay, so if we have nucleophiles with atoms that are in the same column, this might be something like oxygen versus sulfur, etc. Maybe nitrogen versus phosphorus. You know, we're going down the column and we're comparing different atoms. Well, nucleophile strength in this case depends on the solvent that you're using in your reaction. So this is where things can get a little complex, so bear with me. I still get confused sometimes on this. So let's look at the different types of solvents that we use in organic chemistry. And this is a handout on Canvas. It's under Modules Study Guides. And I put it under Chapter 3 initially. So it's part of another handout that we used before. So you can print this out and use this. I'm okay with that. You can use it on quizzes or exams. That's fine with me. So let's look at polar protic solvents first. So the name polar protic tells us that these solvents are polar and that they have a hydrogen bonded to a very electronegative atom. Now, because there's a hydrogen bonded to a very electronegative atom on these solvents, that tells me that these solvents can hydrogen bond. So ethanol, methanol, and water are very common solvents in organic chemistry. The next category is polar aprotic. Now, the aprotic part tells me that these solvents do not have hydrogens bonded to very electronegative atoms, but they're still polar. So these solvents cannot H bond, or they cannot hydrogen bond, but they do have dipole-dipole interactions. So some examples here are acetone, which is what is in nail polish remover. Acetone is a really good solvent for a lot of different things. In fact, sometimes it's too good of a solvent and it's hard to extract your product from it. Acetonitrile is another one. You'll often see dimethyl sulfoxide abbreviated as DMSO. DMF is dimethyl formamide, and you might remember that solvent from one of your pods. And then THF is tetrahydrofuran. So that's another good polar aprotic solvent. And then in the last column, we have nonpolar solvents. So nonpolar solvents cannot hydrogen bond, but they also cannot have dipole-dipole interactions. So really their only intermolecular force are London dispersion forces or van der Waals forces. So some common nonpolar solvents are diethyl ether. We've used that in lab before. Benzene is another one. Toluene is pretty similar to benzene, except it has a methyl group on one side. Dichloromethane is another common solvent. And I know I've gotten a question before about dichloromethane because dichloromethane should be polar, right? Dichloromethane just looks like this, and we have chlorines going down. However, if we look up the electronegativity of chlorine, let's see, let me pull up my electronegativity chart. Chlorine is only slightly more electronegative than carbon. So chlorine's electronegativity value is 3, carbon's is 2.5. So the chlorines are drawing electron density away, but it's actually not enough to create a dipole-dipole interaction. And this is one of those exceptions where, normally we would categorize this as polar, but it actually isn't that polar. So, we're just breaking all the rules that you learned earlier. Sorry about that. We also have chloroform, that's a nonpolar solvent, although we probably don't want to use that in lab because chloroform can make you pass out. So we typically try to avoid that. And then carbon tetrachloride is our last nonpolar solvent that's fairly common in organic chemistry. All right, so let's see how these different solvents will affect the nucleophile strength. So what are the best type of solvents for substitution reactions? So in order to figure out the best type of solvent for SN1 or SN2, we have to consider the transition states. And I'm going to abbreviate transition state as T.S. And then I'm going to put that symbol that we've been using for transition states next to it. So it's a vertical line with two horizontal lines going through it. It almost kind of looks like a telephone pole. Okay, so we're going to consider the transition states for SN1 and SN2 reactions. And basically, we want a solvent that's going to stabilize the transition states. Okay, so let's draw a reaction coordinate diagram for an SN1 reaction. Oh, I'm going to straighten out that line there. It's kind of hard to draw straight lines on an iPad. Oops, I drew a line way down below. There we go. Okay, so let's say we have our reaction coordinate diagram here, and our reactants are, let's say, right here in energy. And remember, in an SN1 reaction, there are two steps. So we have our first step, which is the rate limiting step. Then we form our intermediate. And then we have our second step that goes to the products. So what we're really going to consider here is the transition state for the rate determining step. Okay, so I'm going to erase what I wrote up above, but hopefully you have it in your notes. I just want to make some room for the transition state. So in this transition state for the rate determining step, let's say we have our carbon and it's breaking a bond with the leaving group. And then maybe that carbon is just bonded to random substituents off to the side. So we know that the leaving group is going to be negatively charged once it actually leaves because it takes those shared electrons with it. So that will be partially negative in the transition state because it hasn't fully left yet. And then carbon will be partially positively charged. So I'm going to put brackets around that transition state, and we'll put that little symbol up above. So again, this is for SN1. Now let's look at a reaction coordinate diagram for SN2. So remember, in an SN2 reaction, we only have one step. We go from reactants to products, and we don't have any intermediates. All right, so let's see what the activation energy is, or the transition state. Let's see what the transition state is for an SN2 reaction. So remember when we talked about the role of the nucleophile and the stereochemistry involved in an SN2 reaction, we saw that, my iPad's freaking out today. we saw that the carbon kind of gets stuck in the middle between the leaving group and the nucleophile. So remember, the most stable way for a nucleophile to attack during an SN2 reaction is from behind, so opposite the leaving group. And then let's just say this carbon has some random groups bonded to it here. All right, so this is our transition state for the SN2 reaction. And again, the leaving group is going to be partially negatively charged, but the nucleophile here will also be partially negatively charged. And again, that's why it's favorable for the nucleophile to attack from opposite the leaving group, because that way those two partial negative charges are as far apart as possible. So what we can see here is that both reactions go through a polarized transition state. Okay, so if we want to stabilize the transition state, do we want to use a polar solvent or a non-polar solvent? So remember, like dissolves like. So do we want to dissolve a polar solution or a polar reactant in a polar solvent or a non-polar solvent? A polar solvent. So remember, polar solvents will dissolve polar reactants, non-polar solvents dissolve non-polar reactants. So if we want to stabilize these polar transition states, we need a polar solvent. So polar solvents will stabilize the transition states. So that tells us that substitution reactions are faster in polar solvents because they're more stable in polar solvents. All right. Now, we did see before that there are two different types of polar solvents. There's polar protic and there's polar aprotic solvents. So which one would be best to use? Let's see. Okay, so let's draw a hypothetical situation where we have our negatively charged nucleophile. And let's say we dissolve our nucleophile in a polar protic solvent first. So let's just choose water. Now the hydrogens are going to be attracted to the negative charge because remember, water has its own partial charges. The hydrogens are partially positive, the oxygens are partially negative. So the nucleophile can form hydrogen bonds with the solvent. And I'll just highlight where those hydrogen bonds would occur. Now, if the nucleophile is forming hydrogen bonds with the solvent, does that stabilize the nucleophile, or does that make the nucleophile less stable? So the hydrogen bonds will make the nucleophile more stable. So if the nucleophile is more stable, is it going to react? No, it's going to be surrounded by these strong hydrogen bonds, and it won't really be available to react. So the nucleophile will be less reactive as a result. So what that tells us is that polar protic solvents are not good for SN2 reactions, because remember, SN2 reactions do depend on the nucleophile, because everything happens in one step. The nucleophile attacks as the leaving group leaves. So polar protic solvents are not good for SN2 reactions, which depend on the concentration of the nucleophile. Okay, so what about polar aprotic solvents? So let's just pick one. We'll pick acetone. All right, so acetone would surround the nucleophile in this way, where oxygen's kind of pointing away from the negatively charged nucleophile, because remember, oxygen is more electronegative, so it is pulling electron density towards itself, so it's partially negative. So those oxygens want to be far away from the nucleophile. Okay, so the type of interaction we would have here, so we'll draw a little partial positive charge on the other end of acetone. This would just be dipole-dipole interactions. So we don't have those really strong hydrogen bonds here. So the nucleophile won't be held as tightly by this solvent. So the nucleophile is less tightly held, or we could also say solvated. So that means the nucleophile is still available to react. So polar aprotic solvents are better for SN2 reactions. Okay, so on the last slide we saw that we want a polar solvent for SN2 and SN1 reactions. But then we had to narrow it down to polar protic or polar aprotic. And we saw that polar protic solvents prevent the nucleophile from reacting, and we need that nucleophile in our SN2 reaction right away. So polar protic solvents are not good for SN2 reactions. But polar aprotic solvents don't hold the nucleophile as tightly, so the nucleophile is still available to react. So polar aprotic solvents are better for SN2 reactions. Okay, so let's talk a little bit about SN1 reactions, and then we'll kind of sum up what we just learned. Now remember, nucleophile strength does not matter in SN1 reactions because the nucleophile is not a part of the rate determining step. So nucleophile strength is not important in SN1 reactions. However, we still want to think about the solvent here because we said that the transition state for an SN1 reaction is polar. So we do want a polar solvent for our SN1 reaction, but the solvent interacting with the nucleophile is not what we care about for SN1 because nucleophiles don't really matter for SN1. What we care about is the leaving group. So how does the solvent interact with the leaving group? So we need a solvent that stabilizes the leaving group. Now, let's say our leaving group leaves and it's negatively charged. And let's say our solvent is water for this reaction. So we'll have something kind of similar to what we drew on the last slide. So there's some hydrogen bonding going on if water is our solvent. And then let's say our solvent is acetone. We would just have the dipole-dipole interactions. So which solvent is going to stabilize the leaving group better? Water, right? The polar protic solvent. So the polar protic solvent is better for SN1 reactions. And that's because it stabilizes the leaving group. Now, the acetone can kind of stabilize the leaving group, sort of, but it's better if you have a polar protic solvent that can really come in and hydrogen bond with the leaving group. So overall, polar protic solvents are better for SN1 reactions, and polar aprotic solvents are better for SN2 reactions. That line on the end is very squiggly. All right, so this is a lot to remember, and we went over a lot. This is where I think students start to get a little confused because there's so many things you have to think about and remember. But again, essentially what it comes down to is polar protic solvents will stabilize the leaving group for an SN1 reaction, whereas polar aprotic solvents will stabilize or will not stabilize the nucleophile in an SN2 reaction. So the nucleophile can still react. Okay, and what we'll do in the next video is we'll talk about nucleophile strength in a particular solvent. So it goes even deeper into the interactions going on during a reaction. And then in the next video, we'll go back to our summary table that we've been filling out, and we'll fill out the solvent section. So I'll see you in the next video.